Okay, so this is another video in the series for Math 1224 for UTSA. We are going to be dealing with 2.6 moments and centers of mass. And we're going to start out with something relatively simple, center of mass for two objects in a line. So I've got some numbers picked out. We're going to say at x1, there's a mass of 2 kilograms, and at x2 equals 6, there's a mass of 3 kilograms. So I'm going to make a number line. Let's see, right here. And let's make it horizontal. Yeah. And I'm going to mark out here's 1 and here's 6. Okay. Let's give a little bit more room. So here we've got a mass of 2 kilograms. And here we have a mass of 3 kilograms. Okay. Now, we want to look for the center of mass. So somewhere in the middle, let's just mark it here. Although I don't know for sure, if it's farther here or farther here, that we'll find out. I'm going to mark X bar, the average position. Like, what would be the middle, considering this one is heavier? The average is not going to be 3.5. It's not the average of 1 and 6. It's not going to be exactly between. It'll be a little bit closer to this one, I think, if you think about balancing an object. So what I need to do is think about this. The torque applied by a force is going to be equal to the length of the lever arm, the distance of the object from the fulcrum, times the force that's being applied. So this object, gravity is pulling it down. It's going to want to torque counterclockwise around the fulcrum. Okay. This object, being 3 kilograms on the right, gravity is pulling it down. It's going to want to torque clockwise around the fulcrum. Okay. So this guy, because forces would be in newtons, not in kilograms. 2 kilograms is a mass. I need to multiply by 9.8 and get 19.6 newtons. And over here, multiply and get 29.4 newtons. It's going to turn out that we could use the masses anyway, but we'll go with newtons because that's what this formula says, and then we'll see why we really didn't need to bother with the 9.8 at all. Anyway, the torque applied by this object, okay, is going to be the distance from it to the fulcrum. So x bar minus 1 times the force, the 19.6 newtons. Okay, so x bar, in fact, I'm going to change my stylus to a smaller one. X bar minus 1 times 19.6. And this will be, I guess this will be meters newtons would be the torque unit. Needs to equal this other one. So the distance for this one is 6 minus x bar. That's the distance because we assume that x bar is somewhere between 1 and 6. So 6 minus x bar times 29.4. Now, if we solve this equation, we'll find out what x bar has to be. Where is the center point that balances the forces involved? Before we do that, I want to do something a little bit different because it's going to inform how we do later examples. I'm going to get everything onto one side. I'm going to subtract this onto, to move it to the other side. I'm going to subtract 6 minus x bar times 29.4. Okay, so I'm going to have x bar minus 1 times 19.6 minus 6 minus x bar times 29.4 equals 0. Okay? Now, what I'm going to do is I'm going to distribute this minus sign onto the 6 minus x bar. So I've got x bar minus 1 times 19.6 plus x bar minus 6 times 29.4 equals 0. And again, if we solve this equation, we'll find x bar. But I wanted to observe that instead of having an equation where the left side is made up of the force to the left of the fulcrum and the right side, or the torque rather, to the left of the fulcrum, and then the right side is made up of the torque to the right of the fulcrum, counterclockwise versus clockwise, I can put these both on the same side and just add them up. And x bar minus 1 is, in this case, positive because x bar is between 1 and 6. And here, x bar minus 6 is negative because, of course, x bar is less than 6. So I'm still really subtracting these, but the way I've written it, there's a bit of a symmetry to it, where I just do x bar minus the x coordinate times the force, and then x bar minus the coordinate times the force. And this will work for 3 objects, or 4, or 10. I don't have to, if I have 2 objects and I have one on the left, one on the right, that's fine, but what if I have a bunch of objects? It's going to be more convenient to do it this way. Anyway, now I want to solve for x bar and get a number. So I'm going to distribute, before I do that, I said a moment ago that we didn't really need to use the 9.8 meters per second squared to convert the mass into a weight. Because when I go to solve this equation, I could start by dividing by 9.8 on both sides and just cancel out the 9.8. So I'm going to do that. I'm going to divide by 9.8 on both sides. In fact, I will write that out like this. Okay. So I'm going to have x bar minus 1 times 2 plus x bar minus 6 times 3 equals 0. So I really could have just used the masses to begin with, because if you think about it, gravity doesn't act on the mass on the left differently from the mass on the right. It's pulling the same way on both sides according to the mass. So if I just balance the masses, that's the same thing as balancing the forces. Mathematically, numerically, I get the same result. So in the future, we can just use the masses instead of the forces if we want to. What would not work, of course, is to use the mass here and the force here. That won't work. But if I just ignore forces and only use masses, that will work fine. Okay, so now I can distribute and get 2x bar minus 2 plus 3x bar minus 18 equals 0. Now I can combine, almost running out of room here. I can combine like terms and get, you know what, in fact, let's do this. I am running out of room. So let's do this. So 5x bar minus 8, no, not 8, 20 minus 20 equals 0. Then I can add 20 to both sides and then divide by 5. So x bar equals 4, right? So this is just a little bit closer. Really, this guy should be over here at x equals 4, a little bit closer to this side because it is heavier. So that's an example of how to find the center of mass for 2 objects on a line, especially when they have different masses. Okay, so now let's look at finding the center of mass for several objects on a line. So I have the same 2 objects. I changed the x coordinates. The first object is identical. I changed the position for the next one, and now we have a third object as well. So let's work out what that center of mass is. So I'll make a number line, not because we need it, but it might be helpful to say, okay, here's 1. We're going up to 9. So 2, 3, 4, 5, 6, 7, 8, 9. Kind of equally spaced, good enough. So we've got an object of 2 kilograms here. And then at 3, we have an object of 3 kilograms. And then at 9, we have an object of 7 kilograms. Okay, so there's 2 over here, but this is heavier. It's more than both of them combined. So I'm going to take the same pattern as before. Remember, torque is going to be the distance times the force. And I'm going to say, well, the x bar is somewhere here in the middle, somewhere, right? I think it's probably closer to this, but whatever, the diagram doesn't have to be perfect. So I'm going to say, okay, well, that means for the first object, x bar minus 1 times 2. And I'm using mass in place of force because we could multiply all the masses by 9.8 and then at the end divide out by 9.8. It'll go away anyway, so I don't need to bother with it. I can balance the masses instead of the forces. Plus x bar minus, I didn't label that, 3 times 3 plus x bar minus 9 times 7. And if you just watch the previous example, then this makes sense. But maybe you've paused it and you haven't thought about it in a second. You might wonder, wait a minute. Why am I adding this? Well, remember that x bar is less than 9. So this is negative. So we are subtracting that. Okay, so we are balancing the forces. So now I can distribute. So 2x bar minus 2 plus 3x bar minus 9 plus 7x bar minus 63 equals 0. I can combine like terms, and I get 12 x bar minus 74, I believe. Ah, 70, yeah, 74. Okay. Yeah, 63 and 11, 74 equals 0. Add 74 to both sides, and then divide by 12 on both sides, which is, of course, 37 over 6. If we want a decimal, how much is that? You get a calculator. Well, I'm sorry, that's going to be 6 and 1/6, or 6.167, or if you want, just put a bar over that, right? So we were here at 3, 4, 5, 6, so somewhere like right here is really where we ought to have had that. Something like that. So I had a little too close to the middle. So there you go. That's how you find the center of mass for several objects on a line. And this works for 4, 5, or however many. Okay, so let's look for the center of mass for a thin rod, which has a variable density. Obviously, if it was just like a piece of metal, the center of mass would be in the middle. Like that's easy, right? Let's say it has a variable density. So let's say that the density is let's say rho of x, or if you want, delta of x, if you would rather use delta than rho. Some books use rho, some books use delta. Doesn't really matter, same thing. And let's say this is in newtons per meter, okay? As we talked about before, you can use the mass rather than the force, but we'll go with force, that's fine. So what we're gonna have to do is pick a spot to identify. Well, here's where we guess. Let's say we guess here is x bar, just to have a place to mark out, okay? Now, I'm going to have to chop this into pieces. We're basically going to build a Riemann sum, is what we're essentially doing. So I'm going to identify this chunk of the rod, okay? And let's say this is xi. This is xi minus 1, okay? And I'm going to pick a spot, so let's say in the middle, to identify, oh, this is where we're gonna pick a representative section to say that that's what the mass is defined by. So the density rather. So the density we're going to base upon that position. Okay. Now the force of that's applying to that section that's torquing in this direction around the fulcrum. Okay, that's going to be the length of that section. Okay, length times the density function. Okay, because the denser it is, the basically what we're getting is how much weight is this, right? And the denser it is, the more weight. Maybe it's denser over here and less dense over here, or whichever. Okay, so that's going to be, well, we're going to call this length here. It's a little cluttered. Let's say that this length here is delta x, right? As we usually do, from xi minus 1 to xi is delta x. So the length is going to be delta x times the density rho of xi star. And this is, of course, in newtons, okay? Because we had meters times newtons per meter, we get newtons, okay? And again, or if we want, we can use mass instead of force. That would work out fine. So the distance from the object to the fulcrum, right, from here to there, that's going to be x bar minus xi star. It's the distance from the chunk, the representative part of the chunk, to the fulcrum. So this will equal x bar minus xi star, okay? So the torque for that section is going to equal x bar minus xi star times rho of xi star delta x. Okay, this is the distance, the length of the lever arm. This is the force applying to the object. So this is the torque that's being applied for that chunk. So if I want to say, well, the total torque should be 0 because we're balancing it, right? This should be the center of mass. So I can say that 0 equals the sum as I goes from 1 to n chunks, as we usually do, of, well, each of those sections, right? Adding up, you should get 0 because we've balanced things. So this is the sum as I goes from 1 to n. Oops. Oh, you know, I'm going to need to, I'm going to run out of room pretty quickly. So I'm going to switch to a different stylus. And also, I'm going to shrink this a little bit. And I'll just zoom in and we'll have room. It'll be fine. So of wrong tool. So of x bar minus xi star times rho of xi star delta x, okay? So this equals 0, right? Now, what I want to do, as before, I want to solve for x bar. Like, where is that? Where is that center point? So I'm going to have to use some properties of summations that we utilized previously with Riemann sums. So 0 equals, and I'm going to distribute this onto these two terms. So I'll have x bar times rho of xi star delta x minus xi star times rho of xi star delta x. So sum as I goes from 1 to n of x bar rho xi star delta x minus xi star rho of xi star delta x. Okay. Now I'm going to separate into two sums. I'll have the sum of this stuff here minus the sum of that stuff there. So 0 equals the sum as I goes from 1, it's not very good as I goes from 1 to n of x bar rho xi star delta x minus the sum as I goes from 1 to n of xi star rho of x I star delta x. Now, pause the video and think, what can we do next? What's going to happen next? So, x bar is not a variable as far as the summation is concerned. There's no I. There's only one x bar. So this guy can move out in front of the summation. So 0 equals x bar times the sum as I goes from 1 to n of rho of xi star delta x minus the summation as I goes from 1 to n of xi star times rho of xi star delta x. Okay, I almost out of room. Yeah, so let's go ahead and start a new column up here. And I think I will just copy that. Yeah, okay, so I think I can remember it. So 0 equals x bar times the sum. I might regret that in a minute. Times the summation as I goes from 1 to n of rho xi star delta x minus summation as I goes from 1 to n of x I star times rho of x I star delta x. Let's zoom out. Are those the same? Yeah, okay, cool. So now what I'm going to do is recognize I'm trying to solve for this. This is kind of like I have 0 equals x, oops, x times some number minus some number. So I need to add this to both sides because I'm trying to get x by itself. X bar, really. So the summation as I goes from 1 to n of x I star rho of x I star delta x equals x bar times summation as I goes from 1 to n of rho of x I, oops, getting ahead of myself here, xi star delta x. Okay, so again, it's like we have b equals x times a. What am I going to do? Divide by a, right? So I need to divide this whole summation to move it to the other side. So the sum as I goes from 1 to n of xi star rho of xi star delta x over the sum, as I goes from 1 to n, of rho of xi star delta x equals x bar. So this calculation will estimate where the center of mass is based on using n chunks, right? I take the thin rod and I chop up into n pieces, and then I add up the torques for each piece, and then I solve for delta x. That's essentially what we did with lots of subscripts and stars and stuff like that. But what if I want not an estimate? Because this is, remember, this is assuming certain things. I'm picking, oh, I'm going to say the density is this value here, somewhere in the middle of the chunk. Well, we don't know that the whole chunk is a constant density. Within the chunk, the density is different. So to get the exact value, I need to do a limit. I need to let n go to infinity. So let n go to infinity in both of these, essentially, right? So x bar really equals big fraction the integral from a to b. I probably, need to change my stylus tip again, or just write larger. Let's do this. Okay, so integral, oops, wrong tool, integral from a to b of x rho of x dx over the integral from a to b of rho of x. Okay, so this bottom part is often called the mass m of the object. You're just integrating the density function. Oh, that's the mass, right? This one is often called the moment about the origin. Why is it called moment about the origin? Well, basically we're thinking of this point here. This is where the origin would be, and this is the x-axis, basically, and we're looking at the torque around that point is essentially why it's called that. That will probably make more sense later when we do examples in 2 dimensions rather than just in 1 dimension. Okay, so there we go. This is how you find the, let me zoom out. This is how you find the center of mass of a thin rod with a variable density function. And that's really tiny, but I'll zoom in on it in a second. Anyway, that's the whole procedure altogether. But just to highlight, here is the formula that we'll be using. It's basically MO over M is the calculation. Okay, so find the center of mass of a thin rod that is 5 meters long with density function rho of x equals x plus 1 newtons per meter, with x going from 0 to 5. So we don't necessarily need to draw the thin bar. That did not go quite as I wanted, but I guess I'll take it. But we can say here, x goes from 0 up to 5, right? The density at 0 would be 1, because if you plug 0 into the function, you get 1, so 1 newton per meter. At 5, the density would be 6 newtons per meter. So it's much denser at one end than the other. Okay, so as we worked out before, basically we need to find the mass and then the moment about the origin. So I'm going to do the mass first. So m, this equals the integral from 0 to 5 of rho of x dx, which of course in this case, rho of x is x plus 1 dx. Okay, so this will be x squared over 2 plus x from 0 to 5. So we'll get 25 over 2, so 12 and a half, plus 5 minus 0, so 17.5 would be the total, not mass, but the total weight in this case, because our density function is in newtons per meter. That's a little bit of a misnomer, but that's okay. We'll say mass because we're finding center of mass, although the fact that we have newtons will cancel out when we do newtons over newtons. They cancel when we go to make the ratio. So now I can look for the moment about the origin. So m 0. This is the integral from 0 to 5 of x times rho of x. Okay, so this will be the integral from 0 to 5 of x times x plus 1 dx. So this will be, well, I guess I should distribute first. Integral from 0 to 5 of x squared plus x dx. So this will be x cubed over 3 plus x squared over 2, evaluated at 0 and 5. So we get, what is that, 125 over 3 plus 25 over 2. I'm thinking about 6 already because I want to add the two fractions together. You know what, let's write this guy as 35 over 2 because we're going to have to divide anyway. So we're going to need fractions anyway. So I guess 250 over 6 plus 75 over 6, right? So this is 325 over 6. So x bar, this will be the moment about the origin divided by the mass. So this will be 325 over 6 over 35 over 2. So 325 over 6 times 2 over 35. Can do some cancellation. So this is 3, this is 1. This will be 65 and 7. So when I total that up, I get 65 over 21, or 3 point something, right? 3 point, let's get the calculator out. 65 divided by 21. So 3.095. Okay, so there we go. So the center is just a little past 3. So let's say here's 2.5. So here's 1, here's 2, here's 3, here's 4. So basically, if I get rid of that one, here's 3, and it's just ever so slightly past 3 because the object is denser at this end and lighter at this end. Okay, so that's finding the center of mass of a thin rod with a variable density function. Okay, so let's look at an example of how to find the center of mass for a thin plate, and we'll recycle the concepts that we used in the previous example or two, where we were finding the mass of a thin rod with a variable density. So this has constant density. We'll just think of the density as like being 1 gram per cubic, or sorry, per square centimeter or something. Like it's just a constant density. And we won't really worry too much about how much the weight is, because as we've seen before, that all kind of balances out anyway. You can balance the mass or you can balance the weight. It doesn't ultimately matter. The center is still the center. So basically, if I want to find the center of this object, right, it's somewhere in the middle, right, then I need to do two things. I need to find the center, the x coordinate of the center and the y coordinate of the center. So basically, what I can do is say, well, and I'm just going to sort of eyeball this and not worry about being perfect. I know that, say the center in horizontally is there. That's where x bar is. In fact, let me shorten this up a little bit. So here's x bar, right? How am I going to calculate that? Because I have 2 dimensions. How do I contend with all this stuff up here, the verticality? What I'm going to do is I'm going to imagine this is like sitting on a table, and I am looking at it from below, okay? Or from the side, rather, from the front. Okay, so this is like a cake laid out on a table. And I'm going to look at the cake from the side. So when I look from the side, I'm going to see something like this. Here's the table, right? And then I'm going to have the cake, which I guess I'll try to line it up like this. Okay? All right. So there's the cake. And the y-axis is like right here. I can call it the y-axis, or x equals 0 right there. And because this function is y equals 1 minus x, this x-intercept is 1. So right here, x is 1, okay? And x bar is like right here, okay? And I can think of the fact that there's more if I look basically if I tip my head up a little bit and I can look out and go, oh yeah, there's more over there and there's less over here. This side's denser. There's more stuff, right? And in particular, if you think about, oh, what if this was a big slab of Jello? Then when I look at it, the farther to the left is going to have more thickness to the Jello, more depth to it. And so I look through it, it's going to look darker red. It's like strawberry Jello, right? And on the right, it's relatively thin, so I can see through it really easily. But on the left, it's harder to see through the Jello because it's so thick, and it just seems like it's totally solid. Whereas on the right, I can kind of see through it, and so I'm stalling for time, filling this in, and hopefully you kind of get what I'm talking about. Where the left edge has more Jello, it has more depth to it, right? So I'll think of this as, instead of being thicker, I'll think of this as being denser. Okay, and this one is being lighter. Okay, and I say, oh, what's my density function? Well, how much stuff is there? How much Jello is there? Well, I'll say rho of x equals, well, 1 minus x, because that tells you how much verticality there is over here that corresponds to how much denseness or thickness we have over here. Okay, and all I got to do is the thing we've done already. Find out, well, what's m and what's m0. But since we're now torquing around the y-axis, we'll call this my, okay? So I'll start by finding m. So m equals the integral from 0 to 1 of the density function 1 minus x dx, okay? So this equals, do I have a lot of vertical space? I do, okay. So this equals, well, x minus x squared over 2 evaluated at 0 and 1. So this is 1 minus 1 half minus 0. So this is 1 half. Okay, so that's the mass. Now I want to look for my. What is the tendency to torque around the y-axis? So my, which, yeah, I guess I'll do it here. That's fine. My, this is the moment with respect to the x-axis. So it's the moment along the x-axis, or in other words, the moment around the y-axis. So this is the integral from 0 to 1 of x times the density function 1 minus x dx, just like before in the previous example. So this will be the integral from 0 to 1 of x minus x squared dx. I guess I could have put that up here if I want to conserve vertical space a little bit. Well, no, it doesn't really fit. That's fine. That's okay. So this equals x squared over 2 minus x cubed over 3, evaluated at 0 and at 1. And so that's going to be 1 half, 1 half, minus 1/3, minus 0. So I get 1/6. Okay. So that tells me that x bar, this is my over m. This is 1/6 over 1 half. So that's 1/6 times 2 over 1, which is 1/3. So 1/3, x equals 1/3. That's where the object is balanced horizontally along the x-axis. Okay. Now there's two ways to approach the y bar. So it's gonna be something like this. And you might think, well, of course, this is going to be also 1/3. Well, maybe. I don't want to say it's not. I honestly don't remember. I haven't worked this problem out in a while, so I don't remember. But it seems symmetric to me. So 1/3 seems likely. So I guess one approach is just assume that it's the same. But there's actually two approaches. Now, the one we're going to do, we get to do because this function y equals 1 minus x, this is an invertible function, right? It passes the horizontal line test. So I can write x as a function of y. So I'm going to be able to have a density function as a function of y. That's not always possible. So in a later example, we'll look at, well, what if you can't do that? But for this one, let's let's just go with it that we can do that. And I'm going to look at the cake from the other side. Okay. Now, if it's a cake on a table, then you would still have an image a lot like this one, just the density would be on the other side. I'm going to draw this vertically because I want you to distinguish the vertical from the horizontal. So I'm going to say, I don't know, you're still standing over here, right? You got your feet planted over here, but you're kind of angling your neck and looking at it from the side. If that makes any sense, you're tilting your head to look at the side. Okay. Hopefully that makes some kind of sense. In other words, I'm going to turn the image around, rotating around the y-axis to look at it from this side, but still vertical. Okay. So the cake analogy doesn't work as well, but let's pretend it's like really solid jello. Maybe it's a resin plastic, right? And so it's going to look a little bit like this. So let's see. Oops, that's not what I wanted. Like this. Okay, so there's the y-axis, and I'll make my rectangle, and let's try to size it up. Yeah, let's say that's good. So it's like right here. Okay, and I'm going to colorize this, and there's more thickness at the bottom, so that's where the thickness will be. So I'll color this whole thing in, and then I'll make it denser at the bottom. Okay, cool. So there's the sort of the density is apparent through the colorization. So right here, in fact, I should probably move that over there. Actually, come on. Yeah, that's fine. So right here, this is the x-axis. Okay, and here y equals 1. Here y equals 0. Okay, and so then the moment, or not the moment, sorry, the center in the y-axis is like right there. There's y bar. Okay, so I'm going to do the same calculations. I'm going to find mx, which is the tendency to torque about the x-axis. Okay, so mx, it's basically, well, this would be the integral from 0 to 1 of y times rho of y dy. Well, what's rho of y? Well, I want to get a density function as a function of y. Well, this guy, you can solve for y relatively easily. If I add x to both sides, I get, or rather solve for x, I mean to say, get y as the independent variable. So add x to both sides and subtract y on both sides. So x equals 1 minus y. So that's the density function. So this equals the integral from 0 to 1 of y times 1 minus y dy equals the integral from 0 to 1 of y minus y squared. Oops. It's not the antiderivative. I'm just distributing y minus y squared dy. So the antiderivative of that is y squared over 2 minus y cubed over 3, evaluated at 0 and 1. So I get 1/2 minus 1/3 minus 0, which is of course 1/6. So yeah, we get the same value. That's fine. That's expected in this case. So then y bar, and you might ask, well, wait a minute, we didn't find the mass with respect to y. Well, it's the same mass. It's one object. If we were to redo this calculation with y, well, we would get just the same thing. This problem is chosen to work out conveniently. So y bar, well, this is going to be mx over m. And typically, for most examples, my and mx are typically not the same thing. Just in this case, they are because I chose a relatively simple example to start with. So this equals 1/6 over 1/2, which we've already worked out. This is 1/3. So the center of that that region is 1/3, 1/3. Okay. So that's one approach to find the center of a thin plate or of a region in the plane bounded by a function or more than one function. So next we'll look at, well, what do you do if you don't have a function that is invertible like this one? How do you find mx when you're not able to get a density function in the y direction? Okay, in this example, we're going to find the center of the region bounded by y equals x minus x squared and y equals 0. So the function is a parabola, and I've graphed out part of it. If we identify the vertex, let's say it's right there, then I can go ahead and mark down the x bar, the center x coordinate. So there we go, x bar, done. That was relatively easy. Y bar, and that's because of the symmetry. So we will also look at, but how do you calculate it? So in this case, the work is really in finding y bar. So we're basically going to build a Riemann sum, okay? And I don't want the height to be made with the left or right edge necessarily. So I'm going to make this rectangle kind of large so it's obvious that the height is made in the center, okay? So I'm going to mark the center now as xi star. The right edge is xi, and the left edge is xi minus 1, okay? And of course, delta x is the width. This is xi minus xi minus 1, okay? That's the width of the rectangle. So the height of the rectangle is made up by, in fact, let me change colors here. It's dark blue, but maybe it's more visible than gray on gray. That is going to be f of xi star. Okay. Now we're going to need the center of the rectangle. Let's say it's right here. Okay. The x coordinate is, of course, xi star. The y coordinate is going to be f of xi star over 2. It's half the height of the rectangle, right? So when I want to consider what is the area of that rectangle, f of xi star times delta x, base times height, right? So we talked about before, when you're finding the torque of an object about an axis, you basically just do the distance from the axis times the mass or force that you're calculating. We'll deal with mass only in this context, and we're going to assume uniform density. So the density is basically 1 the entire time. So we're basically dealing with area, because if I say, oh, this region is 1 kilogram per cubic unit, or sorry, per square unit, well, then the area would be also equal to the mass in kilograms. Or if I said, well, actually, for this object, this material, the density is 1 Newton per square meter. Well, then the area gives you the force, the weight involved. So let's just not worry about mass or weight, because we're finding the geometric center, and if we have some multiplier like 9.8 meters per second squared, that'll cancel out anyway. So let's not worry about that. So I'm going to say, okay, the area is that. Now the torque about the y-axis, okay? Well, that's going to be the area times the distance of the center from the y-axis, right? The torque is distance times the force involved. So this will be xi star, so that's the distance of the center from the axis, times the area, f of xi star, times delta x, okay? Now the torque in the x direction, well, that's going to be the distance of the center from the x-axis, which is the y-coordinate of the center, essentially, times the area. So this will be f of xi star over 2 times f of xi star delta x. Okay, so we have the area, the torque about the y-axis, and the torque about the x-axis. So if we take the area, and I guess we'll do it, let me make a little bit more room, actually. Yeah, that'll work. If I take the area and I total the areas, I'm going to get the mass. So M equals, well, let's say M, N. M, the area with N rectangles, right? Well, this is going to be the sum. So I goes from 1 to N of f of xi star delta x. And then I can say, well, we want the exact mass. So m equals the limit as n goes to infinity of the sum as I goes from 1 to n of f of xi star dx, delta x rather. Well, of course, this is an integral, right? The integral from, in this case, from 0 to 1, more broadly a to b, but 0 to 1 of well, that's going to be f of x dx. Okay, so that's how you get the mass. You just integrate the function because we're finding area, really. Now, the torque about the y-axis, we're going to find the moment about the y-axis, and this is the sum as I goes from 1 to n of xi star times f of xi star delta x. But of course, that's an approximation because we've made a number of slices. So what I really want to do is let n go to infinity. So the moment about the, in fact, here, I should call this, what should we call it? M, y, n. The moment about the y-axis with n rectangles. So my was what we'll get if we find the limit of that. The limit as n goes to infinity of the summation as I goes from 1 to n of xi star times f of xi star delta x, which of course this is an integral. It's the integral from 0 to 1, in this case, of x times f of x dx. Okay, and this is probably familiar from the previous example. This is how we calculated that moment. Here's the one that's a little bit different, the torque about the x-axis. So the moment about the x-axis with n rectangles, well, that's the sum as I goes from 1 to n of, well, I have f of xi star over 2 times f of xi star delta x. F of xi star squared over 2, okay? So what we really want is to let n go to infinity. So mx equals the limit as n goes to infinity of the sum as I goes from 1 to n of f of xi star squared over 2 delta x. And again, this is a Riemann sum. So this is the limit, the integral rather, from 0 to 1 of f of x squared over 2 dx. Okay, so now we can calculate, if I want, x bar is the ratio of the moment about y with to the mass. So x bar equals my over m. This is what we've already done. But now y bar, and we've already done it in two ways. We've done it for this example because of the symmetry. We didn't have to calculate all that stuff. But then also in the previous example, this is what we did, the same integral, basically. Y bar, this is mx over m. So if I calculate this integral and divide by the mass, I'll get the y-coordinate of the center of this region, okay? So let's do just that. So I guess what I'll do is I'm going to move all this over to here, and we will work those out. I'll rewrite it here. So m, larger, of course. So m equals the integral from 0 to 1 of f of x dx my, which we don't really need, but we'll do anyway. We'll make sure that we get 0.5, just to be sure that it works the way we expect it to. This is the integral from 0 to 1 of x times f of x dx. And then mx, this is the integral from 0 to 1 of f of x squared over 2 dx. Or if I want, I could put the 1/2 in front, right? 1/2 integral 0 to 1 of f of x squared dx, if I want to do that. So let's do m first. So the mass is the integral from 0 to 1 of x minus x squared dx. Okay, so this equals x squared over 2 minus x cubed over 3, evaluated at 0 and 1. So this will be 1/2 minus 1/3 minus 0, so 1/6. Okay, so we get 1/6 for the mass. Okay, how about my? Well, we're predicting, since we know the x bar is 0.5, it's half of the total interval. We're expecting a result of 1/2. So I'm expecting to get 1/3 here. So this is the integral from 0 to 1 of x times x minus x squared dx. Okay, so this equals the integral from 0 to 1 of x squared minus x cubed dx. So this will be x cubed over 3 minus x to the 4th over 4, evaluated at 0 and 1. So I get, well, get 1/3. Oh, I made a mistake. I said we want 1/3. That's not half of that. It's double. We're expecting 1/12. My mistake. 1/3 minus 1/4 minus 0. And all that equals 1 over 12, which is indeed half of the mass. So that means that x bar, which equals my over m, equals 1 over 12 over 1 over 6, which is 1/2. Okay. So now for the interesting one. What is my? I'm sorry, mx. What is mx? I didn't label this correctly. That's my. Okay, so what is mx? Mx, this is the integral from 0 to 1. Well, I'll put the 1/2 out in front, actually. 1/2 times the integral from 0 to 1 of, well, x minus x squared, right? That's the formula, right? Okay, dx. So this equals 1/2 times the integral from 0 to 1 of, what will that be? X minus 2x cubed plus x to the 4th. If you FOIL that out, x squared minus 2x cubed plus x to the 4th. Yeah, that seems right. Dx. Okay. So that equals 1/2 times x cubed over 3 x cubed over 3 minus, well, x to the 4th over 2, because I'm reducing that as I go, plus x to the 5th over 5. Running out of room here. Evaluated at 0 and at 1. So we get 1/2 times 1/3 minus 1/2 plus 1/5 minus 0. Okay. So that's going to be 1/2 times, well, I'm going to get these all in terms of 30ths, I suppose. So 10 over 30 minus 15 over 30 plus 6 over 30. So I get 1/2 times 1 over 30. So 1 over 60. Okay. So that means that y bar equals mx over m. This will be 1 over 60 over 1/6, which is 1 over 10. So 1 over 10 is the y-coordinate of the center. So on this graph, the center right here, this is often called the centroid. This is 1/2, 1/10. So here's the the basically Riemann sums setup again. Well, sorry, let's do this. There's the setup of the Riemann sums again, if you want to see that. And then here's the work to find all of that. And of course, we didn't really have to find my. It was sort of redundant because we already knew what the x coordinate at the center was. We already knew x bar, but it didn't hurt to see that again. Okay, so let's expand upon that last example. So let's say you have x-axis, y-axis pair, and you've got two functions like this, okay? And you have a region defined by being bounded by those two functions. So I'll kind of shade this in a little bit. We'll do a half-effort job. So basically, we're going to talk about how do you find the moments about x and y for this function. And I'm not going to go through all the detail of the Riemann sums with this one. I'm going to summarize, but you'll get the basic idea, and then we'll just look at, well, what are the formulas? The textbook goes through all the details, but I don't think we need to do all those details twice, since we did it for the case where the bottom function is y equals 0. We don't need to do it again for when the bottom function is some g of x. But yeah, so almost done highlighting this, and then we will get started. All right, good enough. So let's say the top function is f, and the bottom function is g, right? So I'm going to pick and also we're doing the area from A to B, and let's assume for now that the density is just some constant density. Let's not worry about, oh, is it denser here or there? None of the homework problems will do that. So I'm going to pick a representative rectangle, and I'm going to do this slightly differently from the previous one. Again, we're not going to do all the Riemann sum business. We're just going to do this as quick as possible. So let's do it this way. Let's say that this right-hand edge of the rectangle, this is at x, okay? So then the top corner of that rectangle, right, its height level is f of x. And then the bottom right corner, its height level is g of x, right? And let's just say that the center is, let's say that's x tilde, okay? And then the center y coordinate is y tilde, okay? So we're going to use x and y just to refer to the center, basically. But I'm not going to use the tilde in the formulas, though. So that means that y tilde, well, this is going to be approximately, and in the limit, it doesn't, it's all the same in the limit. This is going to be approximately f of x plus g of x over 2. It's the average of the two y coordinates, right? And of course, x tilde is just x in the limit. There's say this is x tilde, right? They're not the same, but when you let n go to infinity, let's not worry about that. Again, I'm not trying to build the Riemann sum. I'm just trying to do the short version of this, since we already went through the details. So that means that m, the mass, this is just going to be the integral from a to b of the function, basically the height, the area, essentially. Again, the area, if this right here is dx, is the width, then the area of the rectangle is going to be the height, f of x minus g of x times dx, okay? So the mass is just the integral of the area, f of x minus g of x dx, okay? The moment about the x-axis, well, let's do y-axis first. The moment about the y-axis, this is going to be the integral from a to b of the distance from the y-axis to the center, right? It's going to be this distance, let me change colors. This distance here, right, times the area. Well, that's x, or x tilde if you want. So x tilde times the area, which is f of x minus g of x dx. And of course, we're going to identify and say, oh, well, x tilde is just called x. In the limit, it's all the same. So this is the integral from a to b of x times f of x minus g of x. And if you think back to the previous example, where our second function was g of x equals 0, well, if this goes away, then there we go, x times f of x, which is how we got the other one. So the moment about the x-axis, well, this would be the integral from a to b of the distance of the center, distance from the center of the rectangle to the x-axis multiplied by the area. Well, what's the distance? Well, from this center down to this axis is y tilde, the center of the rectangle. So this equals y tilde times the area, f of x minus g of x dx. And of course, y tilde is g of x, f of x plus g of x over 2. So this is the integral from a to b of, well, I don't need parentheses, I guess, f of x plus g of x all over 2 times f of x minus g of x dx. And we can rewrite that if we want to say, put the 1/2 out in front, integral from a to b, and I'll do this in 2 stages, f of x plus g of x, in parentheses, times f of x minus g of x. And so we have a product, like a plus b times b minus, a plus b times b minus a. That's not what I meant. A plus b times a minus b, sorry. So if I FOIL this out, I get 1/2 times the integral from a to b of f of x squared minus g of x squared dx. Well, I have an extra parenthesis there. There we go. Yeah. So there is the mass, that integral. There is the moment about y, and then there is the moment about x. And these are all in terms of dx. We don't have any dy's. And the reason is since we have functions, we can't expect that either of these functions is necessarily going to be invertible. It's just not going to work to try to integrate with respect to y. So all of these are integrals with respect to x, which is generally a good thing. If you had functions that were defined differently, you had like you had 2 functions of y, you could still do that. You would just need to reinterpret these functions, or these integrals, sorry, in order to match whatever graph or diagram you had. But basically, these are the formulas that we'll use for the next example and that you would use for the homework assignments. Okay, let's find the center of the region bounded by y equals 2x minus x squared and y equals x, which I've already drawn out. And you can see that the intersection points are at the origin and at 1, 1. So our integrals will all be from 0 to 1. I think first let's start talking about the area of a representative rectangle. So if I draw it out, which we don't have to draw it every time, but sure, why not? Let's draw it this time. So something like, let's go with that. That's fine. It doesn't have to be perfect. So the top end, the height, the top of the rectangle will always be at f of x, and the bottom end will always be at g of x. Okay, and then the width is, of course, always dx. So the area of a representative rectangle is always going to be f of x minus g of x times dx. Okay, so I guess we don't need that over there. Okay, so the mass is going to equal the integral from 0 to 1. So this will be f of x, the top function, 2x. In fact, I need more parentheses there. 2x minus x squared minus the other function, x dx. Okay, so this is the integral 0 to 1. I can combine like terms, x minus x squared dx. Okay, so this will be x squared over 2 minus x cubed over 3 divided at 0 and 1. This number is showing up a lot because we're choosing relatively simple functions. So we get 1/6, as we have a few times. That's all incidental. Then you're not always going to get 1/6. It just turns out for this one, that's what we're getting. So now let's do mx or my. Let's do my. Okay. So this is going to be the integral from 0 to 1 of x times the area. So that'll be 2x minus x squared minus x dx. So this will be the integral from 0 to 1 of x times x minus x squared dx, which equals the integral from 0 to 1 of x squared minus x cubed dx. So that's going to be x cubed over 3 minus x to the 4th over 4, evaluate at 0 and 1. So we get 1/3 minus 1/4 minus 0, which is 1 over 12, which is a repeat from a previous example. Again, that's incidental. So now we can find mx, the moment about the x-axis. So remember, you're doing the distance from the center to the x-axis when you're doing mx. When we did my, we did the distance from the center to the y-axis, which that would be the x-coordinate. Right? If we go back to our diagram here, the center, right? Oh, change the stylus back. The center here, its distance to the y-axis is x. And the distance to the x-axis is the f of x plus g of x over 2. Okay? So this will be the integral from 0 to 1. And I can either go based on the formula that we've quoted before, or I can say, well, let me just do the sum of the two functions. I'll do 2x minus x squared, plus x all over 2, right? The average of the two functions makes the center of the y-coordinate of the center of the rectangle, times 2x minus x squared minus x, okay, dx. Now, alternatively, I'll change colors here. I could have just quoted the formula. Oh, this is 1/2 times the integral from 0 to 1 of 2x minus x squared minus x squared dx. This is the same thing. One, I'm building the integral by using the concept of the distance of the torque, the distance times the area, or I'm just using the formula, and either one's fine. So I'll proceed from this one as though I had not already done that. I guess it's a little redundant though, because I'm kind of gonna just write it again. So 1/2 0 to 1. I'm gonna FOIL this guy with this guy. Okay. So I'll get 2x minus x squared minus x squared. So that's what I meant by redundant. It's that. But if you don't remember the formula, then you can build it the way I've described. So this will be 1/2 times the integral from 0 to 1. So foiling that out will be 4x squared minus 4x cubed plus x to the 4th. I believe that's correct. Okay, that seems right. Minus x squared dx. So this equals 1/2 integral from 0 to 1. We can combine like terms. So 3x squared minus 4x cubed plus x to the 4th dx. So this equals 1/2 times x cubed, that's convenient, minus x to the 4th, that's super convenient, plus x to the 5th over 5, evaluated at 0 and 1. So this is 1/2 times, well, 1 minus 1 plus 1/5 minus 0. And of course, the 1 minus 1 cancels, and I get 1 out of 10. Okay, so that means that x bar equals my over m, which was my is 1/12, m was 1/6, so we get what, 1/2, right? And then y bar, this is mx over m, so this is 1/10 over 1/6. So that's going to be 6 over 10 or 3/5. So the center is 1/2, comma, 3/5. And the integrals weren't that difficult, just polynomials. They're a little bit tedious. All this is tedious, but not super difficult. So the key part is setting up your initial integrals correctly to get the calculation. Anyway, that's probably the last example of this video. In the future, when we get more integration techniques, we have the ability to solve more complicated kinds of integrals. We'll revisit this and do some more examples like this one, just with harder functions, basically.